This topic is chapter 4, under chapter 4, which is heat exchangers. So we are focusing more on the introduction on heat exchanger. So the objectives of this chapter is when you finish studying this chapter, you should be able to, number one, recognize numerous types of heat exchanger and classify them. So we will understand that there are a few types of heat exchanger, and then in these topics or in this chapter, you will understand more on that types of heat exchanger. So number two is to develop an awareness of fouling on surfaces and determine the overall heat transfer coefficients for a heat exchanger. So for you to calculate the thermal analysis, for you to do the thermal analysis in heat exchanger, you have to understand that how to calculate overall heat transfer coefficient, and if there is a fouling in your heat exchanger, then you have to include that fouling factors or fouling resistance into your calculation in order for you to calculate the rate of heat transfer for that heat exchanger. Next is perform a general energy analysis on heat exchanger. In these chapters, you will focusing more on two types of general energy analysis, which are number one is log mean temperature difference method, and the second one is NTU methods. So both of these methods can solve the heat exchanger problems. And next is, like I said before, you will understand about the correlation or relations for you to understand and for you to calculate the rate of heat transfer for the heat exchanger by using these two methods, logarithmic mean temperature difference, or in the short form, in abbreviations, we will call it as LMTD method. And the other one is this one, effective NTU method. So you don't have to worry because I will explain one by one about this method in order for you to understand more on how to perform a general energy analysis. So for the logarithmic mean temperature difference, you will have different types of heat exchanger. Then some of the heat exchanger will have correction factors in order for you to calculate the rate of heat transfer for the heat exchanger. Okay. The last one, know the primary consideration in the selections of heat exchanger. So we focus more first in types of heat exchanger. So different heat transfer applications require different types of hardware and different configurations of heat transfer equipments. So what should we choose? Because we have a few types of heat exchanger. So how do we choose that heat transfer equipment that perfectly suit for our process? Okay, so now we have here we have a very big tank, and then in this tank we have tubes inside. Okay, then normally we have these two types these two types of heat exchanger. The first one is compact heat exchanger. So as we can see here, this is compact heat exchanger, and then the other one is shell and tube heat exchanger. What is the difference between these two? As you can see, for the compact heat exchanger, we have a lot of tubes arranged in that fin. So this is what we call fin. Every each of this plate, we call it as a fin. Sometimes these types, compact heat exchanger, is a cross flow configuration. Okay, in this configuration we have two different kinds of configurations. So we have mixed flow and unmixed flow. What is the difference between mixed and unmixed will be detailed later. And then this is shell and tube heat exchanger. As we can see here, in this shell and tube heat exchanger, we have buffer, this black in color in this heat exchanger. look at my cursor here. So I point into this buffer. So this is what we call as a buffer. So buffer here, we have this buffer to fix the positions of the tubes, and then this line, okay, this line is a tubes, So we have tubes configuration. As we know that before this, we have staggered arrangement, and then we have inline arrangement. So basically that arrangement is in this shell and tube, or in this compact heat exchanger. So based on which of this configuration or arrangement perfectly match to your process. Okay, so at this point, look at this shell and tube heat exchanger. So we have the tube outlet here, and we have tube inlet. The tube inlet will flows a liquid that we want. Either the process is to reduce the temperature or to increase the temperature. So if you want to reduce the temperature, you have to focus more on the shell inlet. So you have to insert the what we call you have to insert, or you have to flow in cold fluid into the shell inlet, because our main fluid that we want to reduce its temperature or increase the temperature is based on the tubes inside lah. Okay, so if you want to increase the fluid, for example, your fluid is glycerin, so you want to increase your glycerin up to from 20 degrees up to 80 degrees. So you have to put it into your tube inlet, and then at tube outlet will be your glycerin at 80 degrees. So your focus is on the tubes. Okay, sometimes you will use the shell side to increase the glycerin temperature. It depends on your application. Okay, so as you can see here in this shell and tube heat exchanger, we have this space. This space is what we call as header. So when the fluid flows in, it will goes into the header first, and after that it will flows into the tube. Okay, so that is a shell and tube heat exchanger. So now we go for a double pipe heat exchanger. We know that this is the first one, compact heat exchanger, and then second one is shell and tube heat exchanger. So third one is double pipe heat exchanger. This is actually a configuration for your experiment, a lab experiment. So you will have this double pipe heat exchanger, or other sometimes we will call it as a concentric heat exchanger. Okay, so we may call it as a double pipe heat exchanger or concentric heat exchanger. So the simplest type of heat exchanger is called the double pipe heat exchanger. So in your lab, okay, we have these kinds of configuration. Okay, double pipe heat exchanger. So one fluid flows through the smaller pipe, while the other fluid flows through the annular space between the two pipes. So two types of flow arrangement. We have parallel flow and then counter flow. So this is the counter flow configuration. So as we can see in this figure, the cold will be in here and then out here. Hot in will be in the tubes. Okay, in the tube. So for the temperature, so we have now we have hot temperature here. So for example, we insert 80 degree Celsius of hot fluid, and then we want to reduce up to 20 degrees Celsius, for example. Okay, so it will reduce the temperature to 20 degrees Celsius. Your graph will be like this for the hot fluid, from high temperature to low temperature. For the cold fluid, so here is the inlet of the cold fluid, and then at maybe we insert it at 0 degrees Celsius, for example, and then it will increase the temperature because there is exchange of heat here. Okay, exchange of heat or exchange of energy inside. So as the fluid move, and it will face this attach or attach to this fluid attached to the tubes, and then the heat transfer will begin. Okay, so either it is into the tubes or out from the tubes. Okay, so in this case we have hot fluid, so the Q will be from inside the tubes to the shell side, so the annular space here. So the Q dot will be from the tubes to outside lah. Okay, so here, because of the transfer of heat or transfer of energy from the hot fluid to the cold fluid, the cold fluid will experiencing increase in energy. So when it increase in energy, we know that energy is directly proportional, or the increase of the energy will reflect to the temperature increase. So the energy transferred to the cold fluid, and cold fluid will experience increase in energy. So increase in energy means that increase in temperature. From 0 degrees Celsius, maybe it will increase up to 20 degrees Celsius. The transfer of heat happens here or occurs here. Okay, so this is parallel counterflow. Counterflow. So for the parallel flow, so we have hot fluid into these tubes, and then cold fluid will be enters at the positions at the same location or at the same direction. Here we have hot in here and cold in here. But here for the parallel flow, it will parallel. So as you can see here, the arrow shows a parallel flow arrangement. So the black arrow and a red arrow. So the cold fluid will enters at 0 degrees Celsius. And then for the hot fluid will enters at 80 degrees Celsius. Okay, as the fluid flows, as the hot fluid flows inside the tubes and out from the tubes, it will decrease the temperature up to 20 degrees Celsius. Okay, for the cold fluid enters at 0 degree, and then it will experience increase in energy, and then it will reflect to the temperature increase in your cold fluid. Therefore, the outlet of the cold fluid will be at 20 degrees Celsius, for example. Okay, maybe because of this have same temperature, therefore maybe we can change it into maybe 15 degrees Celsius, for example, so to make it like this. Okay, so cold fluid enters at 0 degree. As it flows and exchange of heat happens, or exchange of energy from the hot fluid to cold fluid happen or occurs, and then this cold fluid experiencing increase in energy, and it reflects to the temperature increase for the cold fluid. Okay, your graph will be like this. Okay, so what is double pipe heat exchanger? As you know, as you can remember or try to memorize previously in internal heat exchanger, internal force convection, we already introduced you with the annulus, where we have pipe in pipe. So we have a circular pipe and then another pipe in this pipe. Okay, we have pipe 1 and we have another pipe 2. So the annular space is, I change the color of this pen, so into red. So the annular space is here. So this is the annular space. Okay, if you are talking about, or if you are referring to the counterflow, then this will, okay, I draw it like this. Okay, we have another tube inside this tube. Okay, this is a cross section. So you have hot fluid in the tubes. Okay, this is tubes, and then you have cold fluid in this annular space. Okay, and it same goes with this uh, parallel flow. Sorry. So for parallel flow, you have the fluid, hot fluid and cold fluid with the same direction. Okay, that is the two arrangement for the double pipe heat exchanger or concentric heat exchanger. Again, I really like to stress on this annular space. So this is annular. Sorry, annular. Oh, sorry. So this is annular space. Okay, annular space. Annular space. So for the compact heat exchanger, large heat transfer surface area per unit volume. This is the for the heat exchanger. It depends on the heat transfer area to perform the heat exchange mechanism. Okay, so it represents with the area density. So the area density is beta, heat transfer surface of the heat exchanger to volume ratio. So if the area density is higher, then your heat transfer will perform uh, greater. Okay, so for the compact heat exchanger, beta or area density must be more than 700 meter square per meter cubic. So meter square is area per unit volume. So meter cube is volume. So example for the compact heat exchanger, we know that we have car radiator where the beta for the car radiators is 1000 meter square per meter cube. So the large surface area, okay, in compact heat exchanger is obtained by attaching closed space thin plate or corrugated fins to the walls separating the two fluids. Okay, compact heat exchanger are commonly used in gas to gas and gas to liquid heat exchanger to counteract the low heat transfer coefficient associated with gas flow with increased surface area. Okay, in a car radiator, which is a water to air compact heat exchanger, for example, it is no surprise that fins are attached to the air side of the tube surface. Okay, that is the example for the car radiators. The examples. One of the example is car radiators. So we have glass ceramic gas turbine heat exchanger where the beta is 6000 meter square per meter cube. And then the regenerator of Stirling engine, beta is 15,000 meter square per meter cube. And the last one is our our lung, which is a compact heat exchanger, and the area density is 20,000 meter square per meter cube. So this is the design of this is one of the example of compact heat exchanger. So next, compact heat exchanger are commonly used in, like I said before, gas to gas and gas to liquid because of the low heat transfer efficiency. Yeah? So therefore, the compact heat exchanger are perfectly suit the operations of the heat exchange in this process. Okay. Typically, cross-flow configuration, the two fluids move perpendicular to each other. So the cross flow is further classified as, so we have two different cross flow. And one is unmixed flow, and then the other one is mixed flow. What is the difference between these two? The difference is only on the fin. Okay, as we can see here, for the cross flow, this is unmixed, where you can see that so the fin, the plate fin force the fluid to flow through a particular interfin spacing. So we have spacing here and fin. So we have fin, and each of the fin will be the fluid will flow in between the fins. So this is unmixed. So the fluid from this fin to the other fin will not be mixed. Okay. For the cross flow, mixed flow, okay, we know there will be no fin attached to this tube arrangement. Therefore, all the fluids will mix. Okay, this configuration, cross flow, mix, we have fin, interspace fin, and the fluid flow on this interspace fin. Whereas for the cross flow, there will be no fin, so it will be mixed. So that is the difference between cross flow for the unmixed and mixed flow. So for the shell and tube heat exchanger, and this is the most commonly used in industrial application, okay, for the heat exchanger. So large number of tubes are packed in the shell with their axis parallel to that of the shell. So this is the arrangement of the tubes. So we have tubes inside, and this is a tube side for the tubes, and then we have shell side where the fluid flows in the shell of this heat exchanger. Okay, buffers are commonly placed in the shell. Normally, buffers will fix the position of the tubes inside the heat exchanger, and other than that, buffers are normally used in the heat exchanger to create the turbulent flow inside the fluids. Okay, and other than that, buffers also will increase the contact time for the fluid with the tubes. So as we can see here, the flow of the fluids will be longer than we have one big shell, and without baffles we will only have contact time for the fluid with the shell, with the tubes, reduce contact time. Okay, and if we put the baffles, it will increase the contact time, which means that the time for the heat exchanger is enough for them to do the contact time for the fluid will be enough to transfer heat to the fluid. Okay, from the hot fluid to the cold fluid, for example. Okay, shell and tube heat exchangers are relatively large size and weight. So that's why these types of heat exchanger is not suitable for the car radiator. And the car radiator will have what we call limited space, and then shell and tube will not be placed in that space. Okay, in the car. So compact heat exchanger much more suitable for the car radiators, and depends on the operation, where in the car radiator we have air and fluid. Okay, so shell and tube exchangers are further classified according to the number of shells and tube passes involved. So we have one shell and two tube passes, and many more. So it will have a different number of shells and tubes. Okay, so plate and frame heat exchanger. So this is the figure for the plate and frame heat exchanger. So we have these types of heat exchanger consists of series of plates with corrugated flat flow passage. So the hot and cold fluids flow in alternate passage. So these types of heat exchanger suit for liquid to liquid heat exchanger. Okay, provided that the hot and cold fluid streams are at about the same pressure. So the hot and cold fluid in alternate passage is, so we have this plate and then another plate. So in alternate, so first plate is cold and then this insert to this area, and then this cold area will transfer to this third, because this is also cold and this is hot. Okay, hot, and then we have another plate, and then this hot will transfer to the other hot area. Okay, hot plate area. Okay, so this arrangement is alternate passage, called cold hot, cold hot. Okay, alternate. So for the plate and frame heat exchanger, that's all for the introduction for the heat exchanger. And next video will explain more on the general next slide will focus more on the overall heat transfer coefficient and the fouling factors in the heat exchanger. Okay, thank you.